In this example, we want to find the exact length of the polar curve r equals 4 times 2 to the power of theta, for theta values ranging from 0 to 2 pi. Now we know that the formula for arc length in polar coordinates is the integral from a to b of the square root of r squared plus dr d theta squared d theta. So I need to find the derivative dr d theta. Because r is equal to 4 times 2 to the power theta, dr d theta is 4 times 2 to the power theta times the natural log of 2. Now I will work on simplifying r squared plus dr d theta squared, which is the expression we see under the square root in the arc length formula. So we have 4 times 2 to the power theta squared plus 4 times 2 to the power theta natural log of 2 squared. Or in other words, 16 times 2 to the 2 theta plus 16 times 2 to the 2 theta times natural log of 2 squared. Now I notice that I can factor out 16 times 2 to the 2 theta, and my other factor is 1 plus the natural log of 2 squared. So the expression I just found is r squared plus dr d theta squared. So the square root of r squared plus dr d theta squared, which is my integrand, is the square root of the expression we just found, which is 4 times 2 to the theta times the square root of 1 plus natural log of 2 squared. Now I can find the arc length. Using our formula, the length is the integral from 0 to 2 pi of the expression 4 times 2 to the power theta times the square root of 1 plus natural log of 2 squared d theta. I can pull the constants 4 times the square root of 1 plus natural log 2 squared out front of this integral symbol. And then I need to integrate 2 to the theta d theta. This gives us 4 times the square root of 1 plus natural log 2 squared times 1 divided by natural log 2 to the theta, evaluated at 0 and 2 pi. Finally, plugging in the bounds, we get 4 times the square root of 1 plus natural log 2 squared times 1 divided by natural log 2 times 2 to the 2 pi minus 2 to the 0 is 1. So this is our final answer.